takes each item in the iterable and executes the code block once per item. You can terminate the loop early using break or return as described for the while loop. You can terminate a single iteration of the loop using continue as described earlier. The else block is executed when all the iterations are completed. It will not be executed if the loop exits via a break or return. The iterable is anything that complies with Python's iterator protocol. In practice, this is usually a collection such as a list, tuple, or a function that returns a collection of values such as range. The open function returns a file iterator that enables you to loop over a file without phi_rst reading it into memory. It's possible to define your own custom iterable classes too. One common function that is particularly used with for loops is enumerate. This function returns tuples containing both the iterable item and a sequence number that, by default, is equivalent to a list index. This means that the for block can more easily update the iterable directly. Enumerate takes a second optional argument that specifies the sequence starting number, which you could use, for example, to indicate the line number in a file, starting with 1 rather than the 0 default. Here is an example that illustrates some of these points printing a file with associated line numbers. For number, line in enumerate, open, myfile.txt, print, number, \t, line. Finally, Python has a couple of inline loop structures. You saw one of these, the list comprehension, in the discussion of lists earlier in the chapter. A list comprehension is a specify C application of a more general loop form known as a generator expression that you can use where you might otherwise have a sequence of literal values. If you recall the list comprehension example earlier in the chapter, you used it to populate a list with the even squares from 1 to 10, like this. N** n for n in range 1, 11, if not n** n %2, 4, 16, 36, 64, 100. The part inside the square brackets is a generator expression and the general form is as follows. Result expression for loop variable in iterable, if filter expression. Comparing that with the list comprehension example, you see that the result expression was n** n, the loop variable was n, and the iterable was range 1, 11. The filter expression was if not n** n %2. You can rewrite that as a conventional for loop like this. Result equals for n in range 1, 11 if n** n %2, result.append n. 20 Chapter 1 Reviewing Core Python. One important point to appreciate about generator expressions is that they do not generate the whole dataset at once. Rather they generate, hence the name, the data items on demand, which can lead to a signify can't saving in memory resources when dealing with large datasets. You find out more about this later in the chapter when you look at a special type of function called a generator function. Handling exceptions. There are two approaches to detecting errors. The phi_rst involves explicitly checking each action as it's performed, the other attempts the operations and relies on the system generating an error condition or exception if something goes wrong. Although the phi_rst approach is appropriate in some situations, in Python, it's far more common to use the second. Python supports this technique with the try/except/else/finally construct. In its general form, it looks like this. Try, a block of application code. Accept an error type as an exception object, a block of error handling code, else, another block of application code, finally, a block of cleanup code. The accept, else, and finally are all optional, although at least one of accept or finally must exist if a try statement is used. There can be multiple accept clauses, but only one else or finally. You can omit the as part of an accept statement line if the exception details are not required. The try block is executed and, if an error is encountered, the exception class is tested. If an accept statement exists for that type of error, the corresponding block is executed. If multiple exception blocks specify the same exception type, only the phi_rst matching clause is executed. If no matching accept statement is found, the exception is propagated upwards until the top-level interpreter is reached and Python generates its usual traceback error report. Note that an empty accept statement will catch any error type, however, this is usually a bad idea because it hides the occurrence of any unexpected errors. The else block is executed if the try block succeeds without any errors. In practice, the else is rarely used. Regardless of whether an error is caught or propagated, or whether the else clause is executed, the finally clause will always be executed, thus providing an opportunity to release any computing resources in a locked state. This is true even when the try/except clause is left via a break or return statement. You can use a single accept statement to process multiple exception types. You do this by listing the exception classes in a tuple, parentheses are required. The optional exception object contains details of where the exception occurred and provides a string conversion method so that a meaningful error message may be provided by printing the object. It is possible to raise exceptions from your own code. It is also possible to use any of the existing exception types, or to define any your own by subclassing from the exception class. You can also pass arguments to exceptions you raise, and you can access these in the exception object in the except clause using the args attribute of the error object. Getting data in and out of Python 21. Here is an example of raising a standard value error with a custom argument and then catching that error and printing the given argument. Try raise value error, wrong value, accept value error as error, print, error.args. Wrong value, comma. Note that you didn't get a full traceback, only the print output from the accept block. You can also re-raise the original exception after processing by simply calling raise with no arguments. Managing context. Python has the concept of a runtime context. This typically includes a temporary resource of some kind that your program wants to interact with. A typical example might be an open file or a concurrent thread of execution. To handle this, Python uses the keyword with and a context manager protocol. This protocol enables you to define your own context manager classes, but you will mostly use the managers provided by Python. You use a context manager by invoking the with statement. with open file name mode as context name process file here. The context manager ensures the file is closed after use. This is fairly typical of a context manager's role to ensure that valuable resources are freed after use or that proper sharing precautions are taken on FI-RST use. Context managers often remove the need for a try/finally construct. The context lib module provides support for building your own context managers. You have now seen the different types of data that Python can process, as well as the control structures you can use to do that processing. It is now time to find out how to get data into and out of your Python programs, and that is the subject of the next section. Getting data in and out of Python. Basic input and output of data is a major requirement of any programming language. You need to consider how your programs will interact with users and with data stored in files. Interacting with users. To send data to users via stout, you use the print function, which you've seen several times already. You learn how to control the output more precisely in this section. To read data from users, you use the input function, which prompts the user for input and then returns a string of raw characters from stin. The print function is more complex than it FI-RST appears in that it has several optional parameters. At its simplest level, you simply pass a string and print displays it on stout. 22 Chapter 1 Reviewing Core Python. Followed by an end-of-line, EOL, character. The next level of complexity involves passing non-string data that print, then converts to a string, using the str type function, before displaying the result. Stepping up a gear, you can pass multiple items at once to print, and it will convert and display them in turn separated by a space. The previous paragraph identified 3 FI-XED elements in print, s behavior. It displays output on stout. It terminates with an EOL character. It separates items with a space. In fact, none of these are really FI-XED, and print enables you to modify any or all of them using optional parameters. You can change the output by specifying a file argument. The separator is def-ned by the sep argument, and the terminating character is def-ned by the end argument. The following line prints the infamous hello world message, specify ed as 2 strings, to a file using a hyphen separator and the string end as an end marker. With open tmp.txt w as tmp print hello world and equals end sep equals dash file equals tmp. The content of the file should be hello world end. The string format method really comes into its own when combined with print. This combination is capable of presenting your data neatly and clearly separated. In addition, using format can often be more efficient than trying to print a long list of objects and string fragments. There are many examples of how to use format in the Python documentation. You can also communicate with the user using the input function that reads values typed by the user in response to a given on-screen prompt. It is your responsibility to convert the return characters to whatever data type is represented and handle any errors resulting from that conversion. Note in Python version 2, the raw _input function was used instead of input. The version 2 input function behaved rather differently. It evaluated whatever the user typed. This created a security issue because malicious code could be input. The version 2 input function was removed in version 3, and raw _input was renamed to input. Here is an example that asks the user to enter a number. If the number is too high or too low, it prints a warning. This could form the core of a guessing game if you cared to experiment with it. Target equals 66. While true, value equals input, enter an integer between 1 and 100, try. Getting data in and out of Python 23. Value equals int, value, break except value error, print, I said enter an integer. If value target, print, value, is too high, elif int, value, target, print, too low, else, print, pfect. Here the user is provided with a prompt to enter an integer in the appropriate range. The value read is then converted to an integer using int. If the conversion fails, a value error exception is raised, and the error message is then displayed. If the conversion succeeds, you can break out of the while loop and proceed to test it against the target, confident that you have a valid integer. Using text files. Text files are the workhorses of programming when it comes to saving data, and Python supports several functions for dealing with text files. Note the FILO interface in Python is really a specialization of a higher-level abstract interface starting with a class called io.iobase. You can mostly ignore these, they simply create a standardized set of operations that applies to text files and other FILO-like objects. You saw the open function used in previous sections, and it takes a file name and a mode as arguments. The mode can be any of R, W, RW, and a for read, write, and append respectively. Some other modes are less often used. There are also a few optional parameters that control how the data is interpreted, see the documentation for details. The R mode requires the FILO to exist. The W and RW modes create a new empty FILO, or overwrite any existing FILO of the same name. The A mode opens an existing FILO or creates a new empty FILO if a FILO of the specified file name does not already exist. The FILO object returned is also a context manager, and can be used in A with block as you saw in the context manager section. If A with block is not used, you should explicitly close the FILO using the close method when you are finished with it, thus ensuring that any data sitting in memory buffers is sent to the physical FILO on disk. The with construct calls close automatically, which is one of the advantages of using the context manager approach. Once you have an open FILO object, you can use readlines or readline as required. Read reads the entire FILO contents as a single string complete with embedded new line characters. Readlines reads line by line into a list, and the new line characters are retained. Readline reads the next line in the FILO, again retaining the new line. The FILO object is an iterable, so you can use it. 24 Chapter 1 Reviewing Core Python. Directly in a for loop without the need for any of the read methods. The recommended pattern for reading the lines in a file is therefore with open filename mode as file object, for line in file object, hashtag process line. You can write to a writable file object using the write or writelines methods, which are the equivalents to the similarly named read methods. Note that there is no writeline method for writing a single line. If you are using the RW mode, you might want to move to a specify C position in the file to overwrite the existing data. You can find your current position in the file using the tell method. You can go to a specify C position, possibly one you recorded with tell earlier, using the seek method. Seek has several modes of calculating position. The default is simply the offset from the start of the file. You now have all of the basic skills to write working Python programs. However, to tackle larger projects, which are the focus of this book, you will want to extend Python's capabilities. The next section starts to explore how you can do just that. Extending Python. The simplest way of extending Python is by writing your own functions. You can define these in the same file as the code that uses them, or you can create a new module and import the functions from there. You look at modules in the next section. For now you will create the functions and use them in the same file. In fact, you will mostly be using the interactive prompt for the examples in this section. The next step in creating new functionality in Python is to define your own classes and create objects from them. Again, it is common to create classes in modules, and you see how to do so in the next section. The examples here are simple enough that you can just use the Python prompt. Python programmers frequently use documentation strings in their programs. Documentation strings are string literals that are not assigned to a variable and respect the indentation level at which they are defined. You use documentation strings to describe functions, classes, or modules. The help function reads and presents documentation strings. Defining and using functions. Several types of functions are available in Python. This section looks at the standard variety phi_rst, followed by a generator function, and concludes with the slightly enigmatic lambda function. You define functions in Python using the def keyword. The form looks like this. Def function name, parameter 1, param2, function block. Python functions always return a value. You can specify an explicit return value using the return keyword, otherwise, Python returns none by default. If you find the unexpected none values appearing in your output, check that the function concerned has an explicit return statement in its body. You. Extending Python 25. Can give default values to parameters by following the name with an equal sign and the value. You see an example in the odds generator function in the next section. You can most easily understand how a function definition is created and used by trying it out. Try it out creating and using a function. In this try it out, you create a new function that takes several input parameters and returns a value. This function uses the mathematical equation of a straight line to return the corresponding y-coordinate for a given gradient, x-coordinate, and constant. You then use the function to generate a set of coordinates for a line. 1. Start the Python interpreter. 2. Type the following code to define the function. Def straight underscore line, gradient, x, constant. Returns y-coordinate of a straight line dash gradient asterisk x plus constant. Return gradient asterisk x plus constant. Three. Now that you have defined the function, test it using some simple values that you can calculate in your head. Try calling the function with a gradient of 2 and x. 4. Let's now try a more complex test of the for x in range 10. Print x straight 0 minus 3 1. 5. Finally, check that the help function correctly recognizes the function. Help straight underscore 26 chap. How it works. In the phi_rst line in step 2, you created the function definition. You named it straight underscore line and said it had 3 required parameters, gradient, x, and constant. These parameters correspond to the values used in the mathematical equation y equals mx plus c, where m is the gradient and c is a constant. The second line is a documentation string that describes what the function is for and how it should be used. The third line is the function code block. It could be arbitrarily complex and several lines long, but in this case it's a one-liner, and you are returning the result, so you prefix it with the keyword return. Note that the code line has to start at the same indentation level as the start of the documentation string, otherwise, you will get an indentation error. You then tested the function with some simple values. Some mental arithmetic confi RMS that the return value of 5 does indeed equal 2*43. The function seems to work, at least for a simple case. You then used the function to generate a set of x dash y coordinate pairs using a for loop with a phi_xed value for the gradient 2 and constant 3, but supplying the loop variable as x. If you have some paper handy, you can try plotting the coordinates listed to confi rm that they form a straight line. Finally, you use the help function to confi rm that the documentation string was correctly detected and displayed. Generator functions. The next form of function you look at is the generator function. Generator functions look exactly like standard functions except that instead of using return to pass back a value, they use the keyword yield. In theory they can use return in addition to yield, but only the yield expressions produce the generator behavior. The bit of Pythonic magic that makes generator functions special is that they act like a freeze frame camera. When a standard function reaches a return statement, it returns the value, and the function then throws away all of its internal data. The next time the function is called, everything starts off from scratch. The yield statement does something different. It returns a value, just like return does, but it doesn't cause the function to throw away its data. Instead, everything is preserved. The next call of the function picks up from the yield statement, even if that's in the middle of a block or part of a loop. There can even be multiple yield statements in a single function. Because the yield statement can be inside a loop, it is possible to create a function that effectively returns an infinite series of results. Here is an example that returns an incrementing series of odd numbers. Def odds, start equals 1 return all odd numbers from start upwards if int, start, %2 is equal to 0, start equals int, start, plus 1 while true, yield start plus equals 2. Extending Python 27. In this function you rst check that the start argument passed is an odd integer, an even integer divided by 2 has a 0 remainder, and if not, you force it to be the next highest odd integer by adding 1. You then create an infinite while loop. Normally this would be a very bad idea because your program would just block forever. However, because this is a generator function, you are using yield to return the value of start, so the function exits at this point, returning the value of start at this moment in time. The next time the function is called, execution starts right where you left off. So start is increment by 2, and the loop goes round again, yielding the next odd number and exiting the function until the next time. Python ensures that generator functions become iterators so that you can use them in for loops like so. For n in odds, if n7, break else, print n. You use odds, just like a collection. Every time the loop goes around, it calls the generator function and receives the next odd value. You avoid an infinite loop by inserting the break test, so you never call odds beyond 7. Note if you use odds a second time in the same program, it creates a brand new instance of the iterator and the sequence starts over. Now that you understand how generator functions work, you may have realized that the generator expressions introduced earlier in this chapter are effectively just anonymous generator functions. Generator expressions are effectively a disguised form of a generator function without a name. This provides a perfect segue to the phi-NAL function type we will be learning about here, the lambda function. Lambda functions. The term lambda comes from a form of mathematical calculus invented by Alonzo Church. The good news is that you don't need to know anything about the math to use lambda functions. The idea behind a lambda function is that it is an anonymous function block, usually very small, that you can insert into code that then calls the lambda function just like a normal function. Lambda functions are not things you will use often, but they are very handy when you would otherwise have to create a lot of small functions that are used only once. They are often used in GUI or network programming contexts, where the programming toolkit requires a function to call back with a result. A lambda function is definite like this. Lambda param1, param2, param expression. That's the literal word lambda, followed by an optional, comma-separated list of parameter names, a colon, and an arbitrary Python expression that, usually, uses the input parameters. Note that the expression does not have the word return in front of it. 28 Chapter 1 Reviewing Core Python. Some languages allow lambda functions to be arbitrarily complex, however, Python limits you to a single expression. The expression can become quite complex, but in practice it's better to create a standard function if that is the case because it will be easier to read and debug if things go wrong. You can assign lambda functions to variables, in which case those variables look exactly like standard Python function names. For example, here is the straight_line example function re-implemented as a lambda function. Straight_line equals lambda m x c m asterisk x plus c straight_line 2 4 3 5. You see lambda functions popping up later in the book. Just remember that they are simply a concise way to express a short, single expression function. Defining and using classes and objects. Python supports object-oriented programming using a traditional class-based approach. Python classes support multiple inheritance and operator overloading, but not method overloading, as well as the usual mechanisms of encapsulation and message passing. Python classes do not directly implement data hiding, although some naming conventions are used to provide a thin layer of privacy for attributes and to suggest when attributes should not be used directly by clients. Class methods and data are supported as well as the concepts of properties and slots. Classes have both a constructor, __new__, and an initializer, __init__, as well as a destructor mechanism, __del__, although the latter is not always guaranteed to be called. Classes act as namespaces for the methods and data defined therein. Objects are instances of classes. Instances can have their own attributes added after instantiation, although this is not normal practice. A class is defined using the class keyword followed by the class name and a parenthesized list of superclasses. The class defi_ion contains a set of class data and method defi_ions. A method defi_ion has as its phi_rst parameter a reference to the calling instance, traditionally called self. A simple class defi_ion looks like this. Class myClass, object instance _count equals. The class name traditionally starts with an uppercase letter. In Python 3 the superclass is always object unless specify cali stated otherwise, so the use of object as the superclass in the preceding example is actually redundant. The instance _count data item is a class attribute because it. Extending Python 29. Does not appear inside any of the class methods. The __init___ function is the initializer. Constructors are rarely used in Python unless inheriting from a built-in class. It sets the instance variable self, __value, increments the previously defined class variable instance _count, and then prints a message. The double underscores before value indicate that it is effectively private data and should not be used directly. The __init___ method is called automatically by Python immediately after the object is constructed. The instance method a method modifies the instance attribute created in the __init___ method. The __str___ method is a special method used to return a formatted string so that instances passed to the print function, for example, will be printed in a meaningful way. The destructor __del__ decrements the class variable instance _count when the object is destroyed. You can create an instance of the class like this. MyInstance equals myClass 42. This creates an instance in memory and then calls myClass __init__ with the new instance as self and 42 as value. You can call the a method using dot notation like this. MyInstance.a method 66. This is translated to the more explicit invocation. MyClass.a method myInstance 66. And results in the desired behavior whereby the value of the ___ value attribute is adjusted. You can see the __str___ method in action if you print the instance like this. Print myInstance. This should print the message. A myClass instance with value 2772. You could also print the instance _count value before and after creating / destroying an instance. Print myClass.instance_count inst equals myClass 44. Print myClass.instance_count del inst print myClass.instance_count. This should show the count being increment and then later decrement again. There may be a slight delay before the destructor is called during garbage collection, but it should only be a few moments. The __init ___ del and __str___ methods are not the only special methods. Several of these exist, all signify ed by the use of double underscores. They are sometimes called dunder methods. Operator overloading is supported via a set of these special methods including __ed ___, sub ___, mul __, div and so on. Other methods provide for the implementation of Python protocols, such as iteration or context management. You can override. 30 Chapter 1 Reviewing Core Python. These methods in your own classes. You should never def any your own dunder methods, otherwise, future enhancements to Python could break your code. You can override methods in subclasses, and the new defi nitians can invoke the inherited version of the method by using the super function like this. Class subclass parent def __init__, self a value super dot __init__, a value. The call to super __init__, translates to a call to the __init__, method of parent. Using super avoids problems, particularly with multiple inheritance, where a class could be inherited multiple times and you usually don't want it to be initialized more than once. Note the use of super in Python 3 has been greatly simplified compared to its Python 2 form. The super line in Python 2 would look like super subclass self dot __init__, a value, which is much less intuitive to use. Slots are a memory saving device, and you invoke them by using the __slots__, special attribute and providing a list of the object attribute names. Often __slots__, are a premature optimization, and you should use them only if you have a specify C, no need. Properties are another feature available for data attributes. They enable you to make an attribute read-only, or even write-only, by forcing access to be via a set of methods even though the usual method syntax is not used. This is best seen by an example where you create a circle class with a radius attribute and area method. You want the radius value to always be positive, so you don't want clients changing it directly in case they pass a negative value. You also want area to look like a read-only data attribute even though it is implemented as a method. You achieve both objectives by making radius and area properties. Try it out creating a property within a class, testcircle.py. In this try it out, you start by creating a simple circle1 class that has only one attribute and two callable methods, set radius and area. You then create a second class, circle2, which makes radius and area properties. Finally, you see how the use of properties simplify the use of the class in client code. 1. Start your favorite programming editor or IDE and create a new file called testcircle.py, or load the file from the book download site. 2. Enter the following code. Class circle1, def __init__, self, radius self, __, radius equals radius def set radius, self, new value if new value equals 0. Extending Python 31. Self, __, radius equals new value else, raise value error, value must be positive, def area, self return 3.14159 *, self, __, radius 2. Class circle2, def __init__, self, radius self, __, radius equals radius. Def __, set radius, self, new value if new value equals 0, self, __, radius equals new value else, raise value error, value must be positive, radius equals property, none, __, set radius. At property def area, self return 3.14159 *, self, __, radius 2. 3. Save the code. 4. Start the Python interpreter and type the following code to use circle1. Import test circle as tcc1 equals tc, circle 1, 42, C1.area, 5541.764776 print, C1, _ radius, traceback, most recent call last file interactive input, line 1, in module attribute error, circle 1 object has no attribute _ radius C1.set radius, 66, C1.area, 13,684.766039999999 C1.set radius, 4, traceback, most recent call last file interactive input, line 1, in module file d:\python code chapter 1 test circle.py, line 7, in set radius. Else, raise value error, value must be positive, value error, value must be positive. 5. Play with circle 2 using the following code. C2 equals circle 2, 42, C2.area 5541.764776 print, C2.radius, traceback, most recent call last file interactive input, line 1, in module attribute error, unreadable attribute C2.radius equals 12 C2.area 452.38896 C2.radius equals 4 traceback, most recent call last. 32 Chapter 1 Reviewing Core Python. File interactive input, line 1, in module file d:\python code chapter 1 test circle.py, line 18, in _ set radius else, raise value error, value must be positive, value error, value must be positive. How it works. In test circle.py you created two classes. The phi_rst, circle 1, achieved what you wanted to do by forcing the user to change the radius value via the set radius method. You did this by prefishing the attribute self. _ radius with two underscores, which is how Python makes things appear private. You then created the set radius method that validated the supplied value before applying it and raised an error if a negative value was found. You also provided an area method so that the user could evaluate the area using the usual method calling technique. The second class, circle 2, went about things rather differently. It used Python's property defi_nit_ion feature to create an attribute called radius that was write-only. It also created the area method as a read-only attribute. This made the user code for circle 2 much more intuitive, as you saw when you exercised the classes in the interpreter. The key lies in the property type function that you called like this. Radius equals property none _ set radius. This code takes as arguments a set of functions for read, write, and delete, as well as a documentation string. The default value of each is none. In this case you created the radius property with a none-read function, but with the, now private, _ set radius method as a write function. The other values were left at their default of none. The result was that radius could be accessed by the user as if it were a public data attribute when assigning a value, but, under the covers, Python called the _ set radius method. Any attempt to read or delete the attribute would be ignored because the action gets routed to none. The area property is slightly different and uses a Python property decorator at property, which is just a shortcut for creating a read-only property. This is a very common use of properties. Looking at the interactive session, you created a circle 1 instance and printed the area using the area method. You then tried to print the radius directly by accessing _ radius, but Python pretended that it had no such attribute because of the double _ private setting and raised an attribute error. When you used the set radius method, all was well, and printing the area a second time showed that the modify cation worked. Finally, you tried to set a negative radius and, as expected, the method raised a value error exception with a custom error message, value must be positive. In the session using circle 2, you can see how much simpler the code is. You simply evaluate the area property name to get the area, and you assign a value to the radius property name. When you try to assign a negative value, the method again raises a value error. Printing the radius directly again generates an attribute error, although this time it has a slightly different message. Properties require a small amount of extra effort on the programmer's part, but can greatly simplify the usage of the class. Having seen how to extend Python's capabilities using functions and classes, the next section shows you how to enclose these extensions in modules and packages for reusability. Creating and using modules and packages 33. Creating and using modules and packages. Modules are fundamental to most programming environments intended for non-trivial programming tasks. They allow programs to be broken up into manageable chunks and provide a mechanism for code reuse across projects. In Python, modules are simply source fileless, ending in .py and located somewhere that Python can find them. In practice, that means the file must be located in the current working directory or a folder listed in the sys.path variable. You can add your own folders to this path by specifying them in the Python path environment variable for your system or dynamically at runtime. Although modules provide a useful way of packaging up small amounts of source code for reuse, they are not entirely satisfactory for larger projects such as GUI frameworks or mathematical function libraries. For these, Python provides the concept of a package. A package is essentially a folder full of modules. The only requirement is that the folder should contain a file called _init_.py, which may be empty. To the user, a package looks a lot like a module, and the submodules within the package look like module attributes. Using and creating modules. You access modules using the import keyword, which has many variations in Python. The most common forms are shown here. Import a module as an alias import first module, second module, third module. From a module import an object from a module import an object as an alias from a module import first object, second object, third object. From a module import asterisk. The last form imports all the visible names from a module into the current namespace. You'll learn how to control visibility shortly. This carries a signify-can't risk of creating naming conflicts with built-in names or names you have defined or will define locally. It is therefore recommended that you use only the last import form for testing modules at the Python prompt. The small amount of extra typing involved in using the other forms is a small price to pay compared to the confusion that can result from a name clash. The other forms are much safer because you only import specified names and, if necessary, rename them with an alias. This makes clashes with other local names much less likely. Once you import a module using any of the phi-rst3 forms, you can access its contents by prefixing the required name with the module name or alias, using dot notation. You have already seen examples of that in the previous sections. For example, sys.path is an attribute of the sys module. Having said that modules are simply source fileless in practice, you should observe some do's and don'ts when creating modules. You should avoid top-level code that will be run when the module is imported, except, possibly, for some initialization of variables that may depend on the local environment. This means that the code you want to reuse should be packaged as a function or a class. It's also common to provide a test function that exercises all the functions and classes in the module. Module names are also traditionally lowercase only. 34 Chapter 1 Reviewing Core Python. You can control visibility of the objects within your module in one of two ways. The phi-rst is similar to the privacy mechanism used in classes in that you can prefix a name with an underscore. Such names will not be exported when a from x import asterisk style statement is used. The other way to control visibility is to list only the names that you want exported in a top-level variable called __all___. This ensures that only the names you specify cali want to be exported will be, and is recommended over the underscore method if visibility is important to you. Note there is a Python style guide known as PEP8 that provides guidance on naming conventions and code layout rules. Its use is not mandatory, but you are strongly recommended to follow it, especially if submitting code for inclusion in the standard library. PEP8 can be found here. http://legacy http://legacy.python.org/dev/pep/pep0008/.python.org/dev/pep/pep0008/. Note one very important gotcha with modules is that the sys.path list is searched in order. This usually means that any modules you create will be found before the built-in or standard library modules. It is very important that you do not use a standard module name for your own module fileless, otherwise, strange things may happen and, even if you realize that it's your module that's being accessed, other readers are likely to be fooled. You put most of this into practice in the next try it out, but phi-rst, you need to look at packages and how they differ from modules. Using and creating packages. You discovered at the start of this section that a Python package is just a folder with a file called __init___.py. All other Python files within that folder are the modules of the package. Python considers packages as just another type of module, which means that Python packages can contain other packages within them to an arbitrary depth provided each subpackage also has its own __init___.py file. It is a valid package. Note having just said that a package was defined by having an __init___.py, this is not strictly true. The real defining feature of a package is that it has a __path__ attribute. However, in practice, you don't need to provide that because Python does it for you. So, if you create an __init___.py, all will be well. The __init___.py file itself is not particularly special, it is just another Python file, and it will be loaded when you import the package. This means that the file can be empty, in which case importing the package simply gives access to the included modules, or it can have Python code. Creating and using modules and packages 35. Within it like any other module. In particular it can define an __all___ list, as described earlier, to control visibility, effectively enabling a package to have private implementation files that are not exported when a client imports the package. A common requirement when you create a package is to have a set of functions or data shared between all the included modules. You can achieve this by putting the shared code into a module file called, say, common.py at the top level of the package, and having all of the other modules import common. It will be visible to them as part of the package, but if it is not explicitly included in the __all___ list, external consumers of the packages will not see it. When it comes to using a package, you treat it much like any other module. You have all the usual styles of import available, but the naming scheme is extended by using dot notation to specify which submodules you need from the package hierarchy. When you import a submodule using the dot notation, you effectively define two new names, the package and the module. Consider, for example, this statement. Import os.path. This code imports the path submodule of the OS package. But it also makes the whole of the OS module visible as well. You can proceed to access OS functions without having a separate import statement for OS itself. One implication of this is that Python automatically executes all of the __init___.py files that it finds in the imported hierarchy. So in the case of os.path, it executes os __init___.py and then path __init___.py. On the other hand, if you use an alias after the import like this, import os.path as pth, only the os.path module is exposed. If you want to use the os module functions, you will need an explicit import. Although only path is exposed, as the name pth, both os and path __init___.py files will still be run. The Python standard library contains several packages including the os package just mentioned. Others of note include the UI frameworks tkinter and curses, the email package, and the web-focused urlib, HTTP, and HTML packages. You use several of these later in the book. Namespace packages. Python 3.3 introduced a new type of package called a namespace package. A namespace package. Namespace package. 36 Chapter 1. You have now covered all of the theory about modules and packages. In the next section, you put this information to work by creating some modules and a package. Creating an example package. You've read the theory, now it's time to put it into practice. In this section you create a couple of modules and bundle them as a package. You utilize the bitwise logical operators mentioned in the Boolean type section. The intention is to provide a functional interface to those operators and extend their scope to include testing of individual bit values. In doing this you also see several of the Python core language features that were discussed previously. The modules you develop are not optimized for performance, but are designed to illustrate the concepts. However, it would not be difficult to refine any of them into genuinely useful tools. Try it out creating a module, bits.py. In this try it out, you start out by creating a simple, conventional module based on integer inputs. You then create another module that defines a class that can be used to represent a piece of binary data and expose the bitwise functions as methods. Finally, you create a package containing both modules. 1. Create a new folder called bitwise. This eventually becomes your package. 2. In that folder create a Python script called bits.py containing the hashtag. The inputs are integer functions implemented are def not, value, creating an example package 37. Def end, val, def or, val, def xor, def shift left, def shift right, val, def bit, val, idx mask equals 1 idx hashtag all 0 except idx return bool, val and 1. Def set bit, val, idx mask equals 1 idx hashtag all 0 except idx return val, mask. 38 Chapter 1 Reviewing Core Python. 0. The testing of the module throws up some interesting issues. You start off by importing your new module. Because you are in the folder where the file lives, Python can see it without modifying the sys.path value. You start testing with the not function, prefix of course, with the module name, bits, and straightaway you can see an anomaly in that the Python interpreter prints the decimal representation as the result. To get around that, you can use the bin function to convert the number to a binary string representation. However, there is still a problem because the number is negative. This is because Python integers are signed, that is, they can represent positive or negative numbers. Python does this internally by having the leftmost bit represent the sign. By inverting all of the bits, you also creating an testing of the module throws up some. The next set of tests covering the functions and through to shift left should be straightforward, and you can check the results by visually inspecting the input bit patterns and the results. The shift right examples do show one interesting outcome in that shifting the bits too far to the right produces a 0 result. In other words, Python phi LLS the empty space left by the shift operations with zeros. Moving on to the new functionality, you used bit, setbit, and 0-bit to test and modify individual bits within the given value. Again, you can visually inspect the input and result patterns to see that the correct results are produced. Remember that the index parameter counts from 0 starting from the right. Finally, you tested the listBits function. Once more, you can easily compare the binary input pattern with the resultant list of numbers. So you see that you now have a working module that you can import and use just like any other module in Python. You could enhance the module further by providing a test function and wrapping that in an if __name__ clause if you wanted, but for now you can proceed to look at how to move from a single module to a package. Try it out creating a package, bitmask.py. In this try it out. 1. Navigate into your bitwise folder. 2. Create a new file called bitmask.